about two different types of matrices, an identity matrix and an inverse matrix. So to get to the point where we can talk about inverse matrices, we first have to talk about the identity matrix. So we have something called the identity matrix. And the identity matrix is something, if I can get to focus. There we go. The identity matrix would be something like this matrix, this 2x2 matrix, or this 3x3 matrix. And I want you to notice with both of these matrices that in this matrix, there's zeros all the way around the matrix except for along this main diagonal. So if you start in the top right-hand corner and move to the bottom left-hand corner, I said that backwards. If you start in the top left corner and move to the bottom right corner, along that line, there should be only one. So here you start in the top left corner and move across to the bottom right-hand corner, and that's all ones, and everywhere else is zeros. So this diagonal line right here would be called the main diagonal, and that main diagonal is all ones, and everything else in the matrix is zero. So that would be the identity matrix. So the identity matrix is a matrix where the numbers along the main diagonal are all one, and every other entry is zero. Now, we don't want to have to write out the identity matrix every time it's used. So a lot of times the identity matrix will be represented with just the letter I. So if you're looking at a problem and you see the letter I, you know that that stands for an identity matrix. It's just going to depend on what size you need to do whatever operation you're trying to do. So if you follow the rules for addition or follow the rules for multiplication, then you can figure out which identity matrix you need. So it could be a 2x2, a 3x3, it could be a 6x6. It would still follow that same pattern. And there's a special property about the identity matrix. Before we talk about that though, we're going to step away from matrices and talk about just numbers for a second. So if I want to multiply numbers together, say I wanted to multiply 3 times a number and get 3 as the answer. 3 times something equals 3. Well, we know our multiplication facts. We know that this number has to be 1. Same thing, if I wanted to multiply 7 times a number and get 7, we know that for this to be true, this number that I multiplied by 7 has to be 1. So when we're multiplying with just numbers, 1 is a number that anything we multiply by it will give itself. So 3 times 1 is itself. 7 times 1 is itself. So in multiplication, although we don't usually talk about it like this, 1 would be called an identity element because multiplying by that 1 doesn't change anything. When we talk about matrices and matrix multiplication, we also have an identity element, our identity matrix, and when we multiply by the identity matrix, it doesn't change anything. So if I multiply a matrix, let's just call it A for right now, but it's some matrix. If I multiply A times our identity matrix I, whatever size it needs to be, then when I do that multiplication, I should get A as my answer. So I should get the original matrix that I started with. This is also true if we multiply on the other side by I. So if I did I times A, I would get A back. So it doesn't matter where the identity matrix is when you do the multiplication, as long as it's the right size, you should still get just the other matrix back. And this is kind of unique with matrices where I can switch the order that I'm multiplying in. We can't always do that, which is different than most of the multiplication we do. When we're multiplying just numbers, it doesn't matter if we do 2 times 3 or 3 times 2. When we multiply matrices, it does matter what order we multiply them, unless we're multiplying with the identity matrix. That one we know for sure. It doesn't matter with it, whether we multiply on the right side or if we multiply on the left side. So it doesn't matter the order with the identity matrix. So as an example of this property, if we had the matrix 1, 3, 2, 4, 1, 5, we could multiply this by the identity matrix, and we want to make sure we're multiplying it by the matrix that's the correct size. So if we check first the size of this one, this has 2 rows, and then 1, 2, 3 columns. So the first matrix is a 2 by 3. We know the matrix we multiply it by has to have the same number of rows as the first matrix has columns. So this number right here has to be the same as the rows of the second one. So our identity matrix has to have a 3 in the front. And then notice up here, our identity matrices all have the same number of rows and the same number of columns. So this one down here is going to be a 3 by 3, and it's going to be the same identity matrix from up here. So we can multiply this by 1, 0, 0, 0, 1, 0, 0, 0, 1. And if we actually type this into a calculator and try to do this multiplication, our answer would be the same matrix we started with. So it would be 1, 3, 2, 4, 1, 5. So that's that special property with identity matrices. It doesn't matter which order you multiply them in, but when you multiply by the identity matrix, you get the same matrix that you started with. All right, so now that we've talked about identity matrices, we're next going to talk about what's called an inverse matrix. But before we get to inverse matrices, there's a few things we need to define. The first is a square matrix, and this is just a type of matrix. So this is just a way of describing matrix. So a square matrix has the same number of rows and columns. So for example, a 2 by 2 matrix, a 6 by 6 matrix, a 4 by 4 matrix, those would all be square matrices because their rows and columns are the same, or there's the same number of rows and columns. Now, when we have a square matrix, we have something called an inverse. Not always, but sometimes a matrix will have what's called an inverse. So if we have a matrix A, then its inverse, so the matrix A has the inverse A, and then we write it like a power of -1, but when we say this, we would say A inverse. So this is how we would write it in notation. And so sometimes we can have an inverse matrix, and I'll talk to you in just a second about how to find that. But there's a special property for a matrix and its inverse. That's why we talked about the identity matrix first, because when you multiply a matrix by its inverse, you should get the identity matrix. So if I did A times A inverse, then my answer would be the identity matrix, whatever size matrix that needs to be. Same thing, if I did A inverse times A, so I can switch the order here, I would still get the identity matrix I, whatever size that needs to be based on this multiplication problem. So multiplying a matrix by its inverse always gives us the identity matrix. Always. So that's one of those special properties about inverse matrices, and that's going to help us later on as we get to trying to solve equations involving matrices. We'll be able to use this inverse matrix to help us solve those problems. So this is the notation for an inverse matrix, but we also want to be able to do that in the calculator. So to type this in the calculator, you would type your matrix, and then outside of the matrix, you would use a power of -1. So for example, if we want to find the inverse of the matrix, -3, -2, 7, 5, to find the inverse of this matrix, we would type this matrix in our calculator, and you can use an online one like Symbolab. That's the one I've showed you. So you type this matrix into your calculator, then you come outside of the bracket and type a power of -1. Then once you click enter in your calculator, it will give you the answer, and the answer is going to be the inverse matrix. So your inverse matrix here would be -5, -2, 7, 3. So this would be your inverse matrix. And if you multiplied -3, -2, 7, 5 times this matrix, you know that you would get the identity matrix in the end. So this was inverse matrices and identity matrices. Go ahead and make sure you get on Edulastic and look at the assignment there over these two topics. All right, you guys, let me know if you have any questions, and then make it a great day or not. The choice is yours.